Ugh, it's so frustrating.
Jillian says she's going to be a little late, Professor.
Okay, thank you for letting me know. So how did the lecture that I left for Monday work out for you? Did any of you give it a try actually
Yeah,
um,
on Excel.
on Excel? Yeah.
Oh, yeah.
I didn't try. I just watched the video.
Okay.
I
Um,
just watched the video.
what's that?
I just watched the video.
You just watched the video. Um, I'm actually thinking that I might break you up into groups and have you help each other through the whole what? What's so funny? Okay. Um, have you help each other through that. But I think I want to talk about something else first before we go back to the whole traffic problem. So traffic problem, I think we have more or less thoroughly explored for now, and there's some very interesting stuff going on that you'll see shortly. Some very interesting phenomena that relate to things that you have certainly seen in the real world, even if you don't actually drive. But I want to talk about the idea, this very basic idea that the amount of something in a cell at time t plus 1 is sort of a function of three things. The amount that was in that same cell at time t, the amount that entered between time t and time t plus 1, and the amount that left between time t and t plus 1. So we used this idea, this very basic idea, when we were coming up with our traffic model. So we had like the density in cell I at time t plus 1 was equal to, remember we said this was basically the number of cars, since each of our cells were 1 mile long, was the density in that same cell at time t plus the number of cars that entered, minus the number of cars that left. The number of cars in the cell at time t plus 1 was the number of cars that were there in the previous time period, plus the number of cars that entered, minus the number of cars that left. This should be visceral. I don't mean to insult you, but you should be looking at that and going, duh, of course, that makes sense. That should feel so at home in your gut that writing it down almost doesn't seem worthwhile. Is that okay? So I want to explain that this is a very general principle that we can use when we model a lot of things. Now, I want to take a look at a situation right now that's a version of something, for those of you that have taken a course in, let's say, differential equations. How many of you have taken the differential equations course? One.
Taking it now.
Taking it now. Okay, so you're taking it now. One of you's already taken it. This is probably a situation that you've seen in a differential equations course. We're going to avoid differential equations right now, so we're not going to make time continuous. We'll have time be discrete right now. But let's just say that, so for those of you that have already taken it, I think Sam, you said you took it already, and Jackson, you're taking it now. Have you done problems with like interconnected tanks of solutions? This tank is pumping into this tank, and so on. So we're going to do exactly that, except we're not going to consider time to be continuous. Can I erase this? You got this all? Okay. So here's the deal. Let's say we have tanks connected like this. So we'll have, like, say, 3 tanks. And let's say the amount in each tank is constant. Let's say 1,000 liters here, 1,000 liters here, and 1,000 liters here. And we'll put little stirrers in the bottom of the tank. They keep everything in the tank homogeneous. Yeah. These arrows inside. And let's say initially, tank one contains saline solution of concentration, let's say 50 grams per liter. Of salt. So in each liter of water, there are 50 grams of salt dissolved. And tank 2 and tank 3 contain pure water.
What's the word before 50 grams?
Concentration. Concentration. So initially, tank 1 contains a saline solution of concentration 50 grams per liter of salt. So every liter of water has 50 grams of salt dissolved in it. Initially, tank 2 and tank 3 contain pure water. So if this was a differential equations class, we would treat time as if it were a continuous variable. So in other words, we'd be pumping water into tank 1, and water would be pumping in from tank 1 to tank 2, and from tank 2 to tank 3, sort of at a constant rate. Like you'd have these pumps running all the time. And we'd want to know what's happening in terms of the concentration of the various tanks over time. But we're not going to treat time as if it's continuous. What we're going to do is break time into 1-minute increments. One-minute increments. Every minute, this is what happens. we release 100 liters of water from tank 3. Sorry, 100 liters of solution. So 100 liters of solution just go out the drain pipe. We flush 100 liters of solution from tank 2 to tank 3. We flush 100 liters of solution from tank 1 to tank 2. We fill tank 1 with 100 liters of fresh water. And then we stir all tanks to homogenize them again. So we do it in this order. And then things are just quiescent until the next minute happens.
What's 5, Professor? It's a little out of the screen.
Oh, sorry. We stir all tanks.
Stir. Okay, cool. Thank you.
Oh, yeah, I see the problem. Okay, hang on. Somehow my webcam got disturbed. Not that it was a very good webcam to begin with, but now it seems to be worse. Okay. So every minute we come in and this gets flushed, 100 liters of water leave, then 100 liters of water go from here to here, then from here to here, then we put 100 liters of water in here. So now all tanks are back to 1,000 liters, and then we stir all the tanks. Everybody got that? Awesome. Okay. And of course, what we want to know is what happens to the concentration of salt in each tank over time. And again, for those of you that have done a differential equations course, you see that what we've done here is we've taken a continuous problem, and by breaking things up into minute intervals and saying things happen in this order, we've made it discrete. Can I erase what's over on this side? Or anybody still working on it? By the way, I want to tell you that for those of you that have your cameras on, I appreciate it. And for those of you that have your cameras off, I understand that there may be reasons why you don't have it on, and that's fine too. But it is much easier for me to see faces, at least some of them, as I'm lecturing. So let's come up with some variables. Let's let CIT be the concentration of salt in tank I at time t minutes. And of course, our initial conditions, given in the problem, are C of 1, 0. Tank 1 at time 0 is going to be 50 grams per liter. C of 2, 0 is going to be 0 grams per liter because it contains pure water initially. And C of 3, 0 is going to be 0 grams per liter. Now, I'm going to ask you this. I'm going to ask you to think about this quietly for a moment so everybody has a shot to think about it. But just sort of qualitatively speaking, ask yourself what's going to happen over time in the various tanks. Now, I know that some of you want to answer right away, and that's great. Just hold on to your thoughts for a moment. Let's give everybody a chance to think this over. Qualitatively speaking. Is everybody giving it some thought? You can try. Oh, so what? So why don't you try to put your thoughts into words? Yes, Jackson.
Like eventually all of them are just going to be pure water.
Eventually, all of them will be approaching pure water, right? I mean, I don't know if there will be pure water, but they'll be getting less and less salty. What happens in the short term? Does anybody else want to answer sort of in the short term what happens?
Tank 2 and 3 are going to increase their concentrations of salt.
Yeah, for a while, tank 2 and tank 3, the concentrations of salt are going to be going up. Which one is going to go up first?
Tank 2.
Tank 2, and then eventually tank 3 will go up, and they'll go up for a little while, and then it'll start dropping again. Tank 1, I think you can see, since we're flushing with pure water the whole time, it's going to just sort of steadily drop. Now, let me ask you this. As we said, the concentration of salt in tank 2 is going to be going up for a little while, and then it's going to be dropping. What has to be true about the concentration of salt in tank 2 and tank 1 when the concentration of salt in tank 2 starts to drop?
They have to be equilibrium.
Well, I don't know if we're going to hit equilibrium right now. So the equilibrium, I think, is going to be where everything is pure water, and we'll approach equilibrium. But so we said tank 2 is going to be going up for a while. So the concentration of salt in tank 2 is going to be going up for a while, and then it's going to start to drop. What has to be true about the concentration of salt in tank 1 and tank 2 when it starts to go down in tank 2?
More salt is exiting tank 2 than entering.
Right. And so what can you tell me about the concentrations of salt in tank 1 and tank 2?
They'll be equal.
They'll look past the point where they're equal, and at first the concentration of salt in tank 1 is going to be higher than the concentration of salt in tank 2, and so more salt will be entering than leaving. But after a certain point, the concentration of salt in tank 1 will be lower than the concentration of salt in tank 2. So we can do this all in an Excel spreadsheet. It's not all that bad. Maybe we can put in like zeros for, the pure water coming in here. And we can have a column for tank 1, column for tank 2, column for tank 3. And initially, there is a concentration of 50 in tank 1, 0 in tank 2, 0 in tank 3. And then as you know, this will be like time 0, time 1, time 2, time 3. And so at time 1, we could go ahead and figure out what the concentrations are. But more interestingly for Excel, if we could come up with propagation equations, then we could just plug those in and figure out, what the concentrations of salt are at time 1, time 2, time 3, all the way up to like time 100 if we wanted, fairly easily. So the question is, what are the propagation equations? And my hint to you is that the propagation equations go back to that same concept we were talking about with traffic. The amount of salt, so we have to get it clear in our head, the relationship between the amount of salt in a tank and the concentration of salt in a tank. It might be easier for us to think for a while in terms of amount of salt, total weight of the salt, total mass of the salt in terms of in a tank, and then go back to concentration later. So for instance, what's the mass of salt in tank 1 initially? If we have 1,000 liters and we have 50 grams of salt per liter, how much salt is in that tank? What's the mass of salt in that tank initially?
50,000 grams.
50,000 grams of salt, exactly. You just took 50 grams of salt per liter. There are 1,000 liters. There are 50,000 grams of salt in that tank initially. So maybe it's easier for you to work in terms of amount of salt, 50,000, 0, 0. Maybe it's easier to work in terms of concentration of salt. Since the tanks each have 1,000 liters, the concentration of salt is always going to be 1/1000th of the amount of salt in there. But I am going to go ahead and break you up into groups now, and I want you to try to come up with propagation equations and run this thing in Excel and see what you get. So let's see, we have 11 of you. No, there are 11 people, and I'm 2 of them. So that means 9 of you. So I think groups of 3? How's that sound? So, oh wait, something's in the chat. What's in the chat? Oh, thank you. breakout rooms. Into 3 breakout rooms. 8 rooms. Okay, hang on, let's try that again. Because I am counting as one person over here, so I'm gonna get rid of me over here. And now let's do this again. It's just going to break you up randomly. There we go. Okay, here we go. And boom. Wait, did I do it wrong? Try that again. Okay, I think I got it now.
Hey, Professor Ordor.
Hey there. Hang on. My computer's being stinky again. I can't see you. Where are you? You can see me, right?
Yeah.
Yes.
How's it going, by the way?
It's going well. I think we have a pretty solid theory of what happens to the concentration over time in each tank. I don't think we've, as of yet, quite.
Sorry, you keep fading out.
I said I think we got a solid theory going on how the concentrations change over time in each tank, but we haven't built our propagation equations yet.
Oh, okay. I'll let you work on that, and I can't get out of here.
When so Brandon.
Yeah.
So when we're building these equations, almost like the volume of water in the tank is almost irrelevant. Like I
Yeah.
feel like you could almost build the equations based off just the concentration of salt. And
Yeah, that was entirely my thought process on it, and the way that I attempted to get it to work in Excel.
I guess like the only important part about the volumes of water is that they're each 1,000 liters and they're losing 100 liters to give us like a clear 10%, 10% of like the mixture leaving each time.
Yeah.
Okay, I'm gonna leave you guys to it. I'm gonna go to breakout room 2.
There he is.
Hi there. Sorry about that. I am having trouble with my computer again. But I think I can. Okay, now I see you. So how's it going so far?
We're a little confused.
Okay.
We've been trying to like talk it out, but we don't
Good.
know where to start, really.
So maybe instead of working with concentration, work with like amount. So start off with like 50,000 grams of salt in tank 1 and 0 in tank 2 and 0 in tank 3.
I got this chart. I don't know if it's right or if you can see it at all.
55, so 5, 45, 0. So
And then when
it's
you reach equilibrium, it would go into 3.
so you're in your time period 1, what you have there is exactly right. You'll have 45 in tank 1 and 5 in tank. What's that?
It's in thousands as well, right? Yeah.
No, but it's still right. I mean, I know what you're talking about. But at time 2, it's not right anymore. For one thing, there'll be some salt in tank 3 by time 2.
So would it be the 45 and then 5?
For time 1, it's 45 and 5. But for time 2, it's not. I think you had 40 and 10.
Yeah.
And it's not that, because we're flushing salt from tank 2 into tank 3. I mean, there's no salt in tank 2 in time 0 to get into tank 3 in time 1, but there is salt in tank 2 to go into tank 3 at time 1. Plus, the amount of salt in tank 1 at time 2 is not going to be 40, because there's not as much salt there, so not as much salt leaves between time 1 and time 2.
Got it.
So you had your initial quantities right, and the quantities at the next time period you had right. But after that, it's not quite right. So if you can work out maybe the next one, I think that might help you with propagation equations.
So would it be like, let me write it down real quick.
Actually, so good.
Just add it. Oh.
That's fine.
Would it be 4.5?
You mean in tank 2?
Yeah.
No, that was a great, I mean, that takes into account how much was there and how much left. But don't forget some more arrives.
Yeah.
So it does go up, it just doesn't go up to 10. Why don't you figure out how much is in tank 1 at time 2? That might be the easiest thing. So how did you get from the 50 to 45?
It was transferring over 100 liters, and it had 50 grams salt.
Right. So what you just said is that like 10% of it left.
Mm-hmm.
Right? 10% of the amount of salt left. So in the next time period, 10% is going to leave again.
So it'll be 30. Oh, wait.
No, it's going to be more than 40.
Let's see. 40.5.
Yep. Okay, I think you have it now. I think you have an idea of what's going on. So see if you can take that intuitive understanding now and turn it into propagation equations.
Sorry. Before you go,
Yeah.
would at time 2 would tank 3 be 5?
No, it's not 5 because there wasn't that much salt.
Okay. Yeah.
Okay, I think you're converging on the right answer now. I think you're getting closer and closer.
Okay.
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 So talk it over amongst each other, amongst yourselves.
Okay. Thank you.
Welcome.
Hey, Professor.
Hey there. Hey,
I
hey,
think-
I need to find you. My computer is being so stinky. So
You're good.
where are you? Oh, somebody's sharing a screen right now.
Yeah,
Yeah,
it was
we
me.
did it.
Okay, so 45, 50, then 40.5, good. And then, so can you show me your propagation equation in cell C3? C2 plus B2. Good, and what do you got in the next tank? You guys got this. I don't even know. You didn't need me. Yeah, that's. Yeah, go ahead.
We got this by, we basically got this value by dividing the outflow by the initial concentration.
I see exactly what you did. I'm looking at your answer and I can see what your thought process is. This is great. I mean, yeah, I see even how you wrote it. You wrote it, amount that was there before plus the amount that enters minus the amount that leaves, and you got it all. And then, as you said, you switched back and forth between concentration and amount. This is beautiful. So let's see what happens over time. So it starts to
Our turning
one
points
would
are
just
at
change.
10 and 20 minutes.
Yeah, there isn't very much left.
Yeah, there's always going to be a little bit because it's just constantly dividing.
Right, exactly. Great. Okay, well, I will tell you, don't the other groups are not going as fast as you. You basically finished, so but they're still working on it. So we'll get everybody back together briefly. What time is it? Oh, I guess I better end breakout rooms now.
Yeah, you got
And-
like 60 seconds.
Yeah, I got it. 2 seconds. So hang on. Close all rooms.
That was funny, Sam.
Dude, I think I'm gonna watch regular show now after you remind me of it. I'm gonna probably take a break some later day and watch some regular show.
I know. After this, I'm gonna make some breakfast. Well, lunch, but
Yeah, I ate breakfast right before this.
What are we eating, Jalen?
I don't know yet.
Oh, okay.
Probably an omelet. I don't know.
Sounds good.
I had-
like in mind.
I had leftover biscuits and gravy.
I had
Awesome.
pumpkin cranberry bread
Awesome.
and pumpkin spice coffee. Feeling festive today.
I had pumpkin spice beer last night. This was really good.
No.
It wasn't like ridiculously sweet like most pumpkin spice stuff is. It was more like a hint of pumpkin spice in the beer. Like it was really good.
So
Sounds delicious.
actually, based on this conversation, what I often do with my like most senior level class in a semester, which you guys are, is I'll have my class over for lunch, which I clearly can't do for obvious reasons. But would you all like to have one class where we all sort of have lunch together while we're having class?
Sure.
Sure.
If it fits into the schedule.
Well, I mean, it just means we have to eat, at 11 o'clock, which might be a little.
I do that anyway.
Is that something you'd be interested in?
Yeah.
Okay, okay, great. So we'll do that at some point. But I see I've already gone overtime, and I apologize for all the trouble that I'm having with my computer this morning. I'll see if I can figure this out before Friday's class. Yeah, but that's it. I will see you all on Friday, and we'll talk a little bit more about this, talk a little bit more traffic, and then we'll go to something else.
Awesome.
Okay. Laters.
Bye.
Bye.